In Hello. In this section, we will be talking about inverse functions. An inverse function is really defined as a function that does exactly the opposite of another function. And essentially the way that happens is that you come up with a new function where all the x values of the original function become the y values of the new function and vice versa. Okay. So, not every function has an inverse. The only functions that have inverses are functions that are referred to as one-to-one functions. So we'll start this section by going over the definition of a one-to-one function and then looking at a few examples. So a one-to-one function is a function f is a one-to-one function if for a and b in the domain of f, if a is not equal to b, then f of a is not equal to f of b, or equivalently, if f of a equals f of b, then a equals b. So both of those conditions have to be met in order for it to be a one-to-one function. Now, when we first defined functions earlier in the class, what we said was that on its most fundamental level, a function is a set of ordered pairs where all of the x values are unique. Okay, so like if we come down here to example number 1, we see a set of ordered pairs and the x values are all unique, right? This ordered pair has an x value of 2. Here we have an x value of 4, an x value of 7, an x value of -2. They're all unique. Okay. Now a one-to-one function has the additional requirement that all of the y values also have to be unique. Okay. So in question number 1, this set of ordered pairs, it does represent a function, but it does not represent a one-to-one function. And the reason for that is because we have two ordered pairs, 2, 1, and -2, 1, that have the same y value, right? So it's a function, but not a one-to-one function. If you have a function and you want to find its inverse, what you do is you just interchange the x and the y values. And if I do that here, again, it illustrates the point why this function does not have an inverse, because if I interchange all the x and the y values, I will get here, this one becomes 1, 2. Oh, sorry about that. Let me fix that. Okay. 1, 2. Okay. And then I get 4. Oops. Sorry. I'm just messing up like crazy today. If I switch them around, then I will get 2, 4. And then I will get 3, 7. And then 1, -2, right? So that's how you find the inverse of a function. However, in this case, when I interchange the x and the y values, the set of ordered pairs I come up with no longer represents a function, right? Because now I have two ordered pairs that have the same x value. And that can't happen in order for it to be a function. It is a relation, but not a function. Over here in question number 2, right, we have an example where it does not utilize numbers, right, but the same idea applies. The first oval here would represent the domain, the second oval the range. Batman maps to Joker, Green Lantern maps to Sinestro, Wolverine maps to Sabretooth. And so what you see is that there are 3 unique values in the domain and each value in the domain maps to one specific unique value in the range, right? So all the x values are unique and all the y values are unique. So yes, this does represent a one-to-one function. Now here. Now back when we introduced functions originally, we talked about the vertical line test, where you could look at the graph of a function, and if you could draw a vertical line, right, and if vertical lines never intersect the graph more than once, then the graph represents a function, right? So all three of these graphs that you see on the screen right here, these are all graphs of functions, right? So like if you picture drawing a vertical line on any of these graphs, no matter where you draw the vertical line, that vertical line will never intersect the graph more than one time, okay? Now a one-to-one function has to pass the vertical line test, but it also has to pass the horizontal line test. In other words, a function y equals f of x is a one-to-one function if no horizontal line intersects the graph in more than one place, right? So like in this one right here, this one is just a series of dots, but no matter where I draw the horizontal line, it's never going to intersect any of the dots more than once, right? So that does represent a one-to-one function. Whereas over in this one, right, if I draw a horizontal line, it intersects the graph at several points. So that is not a one-to-one function. That graph does not represent a one-to-one function. And then finally over here, with this one, right, no matter where I draw the graph, no matter where I draw a horizontal line, again, it never intersects the graph more than once. So the graph in the middle does not represent a one-to-one function. The other two graphs do. So let's say we want to take a look at a function, and we want to determine whether that represents a one-to-one function or not. Okay. Now remember, at the very beginning, we kind of defined the conditions that have to be met in order for a one-to-one function, in order for a function to qualify as one-to-one. Okay, and those conditions are either you could say either if f of a equals f of b, then a equals b. Okay, so that's one condition. The other one is if a is not equal to b, then f of a is not equal to f of b. Okay, so I could choose one of these conditions and use it as a test. Let's choose this first one. Basically, if you evaluate f of a would be 3a plus 2. F of b would be 3b plus 2. And I would want to simplify this down to see if it simplifies down into the statement a equals b. So if I subtract 2 from both sides, I get 3a equals 3b. And then if you divide both sides by 3, you get a equals b. So it does indeed simplify down into that. So we would say that yes, this is a one-to-one function. Okay, that's basically a proof. But what about over here? This one? Let's try something similar, right? So F of A would be 3A squared. F of B would be 3B squared. If I divide both sides by 3, I get A squared equals B squared. Okay. And then if you were to take the square root of both sides, you would get A equals plus or minus B, right? There's two roots. And so basically the conditions that, we've got A equals B, but we also have A equals negative B, right? So it does not simplify down into this exact statement A equals B, right? So this one is not one-to-one. And even by looking at the functions, we should be able to kind of know that also by visualizing the graph. This is a linear function, so it's going to be a straight line with a slope of 3. Positive slope, right? The graph will look something like that. And so it will pass the horizontal line test, right? Oopsie, sorry, over here. This is a parabola, because it's a quadratic parabola that opens up, right? Because it's positive. Parabolas will be something like that. And you can see that would fail the horizontal line test, right? So visualizing the graph is also another way of determining that this one, f of x equals 3x squared, is not one-to-one. F of x equals 3x plus 2 is one-to-one. Okay, so what we said is that a one-to-one function is a type of function that has an inverse. And an inverse function is a function that does exactly the opposite of the original function. Okay? So here is a test you can apply to determine whether two functions are inverses of each other, is by using the function composition method that we've looked at earlier in the class. If we let f be a one-to-one function, then g, and then if we define g as the inverse of f, the following conditions are both true. If we compose the functions both ways, the result is just going to be x, right? And this actually kind of makes sense, right? Because this notation here, we define that as f of g of x, right? This has to equal x. This is g of f of x, right? And this has to equal x. This is basically, this first one we're saying the output of g serves as the input of f, right? So if the functions do exactly the opposite, then when we take the output of g and plug it into f, f is basically undoing g, and you just get right back with what you started with, right, which is x. And it's going to work both ways if the functions are inverses, if they do exactly the opposite of each other, right? If we take the output of f, plug that into g, well, g is basically undoing f, right? So you're just going to get right back with what you started, which is x. So both of these conditions have to be met in order for a function to be, in order for two functions to be inverses of each other. Also, typically, the notation we use for an inverse function is this superscript notation, right? So it kind of looks like an exponent, but it's really just a notational thing. This f superscript -1 of x, that's the standard notation that we use to represent an inverse, right? So if f of x is a function, the f with the superscript -1 of x, that represents the inverse of the function f, okay? So if you compose a function with its inverse in either direction, the result will always be x. Let's take a look at a couple of examples. Determine whether the two functions are inverses. Okay. So in number 8 here, we have f of x equals 3x plus 6. G of x equals 1/3 x minus 2. Okay, so let's start with these. So if we compose in this direction, okay, this is equal to f of g of x, which equals f of 1/3 x minus 2. And so in the function f, the x has to get replaced with 1/3 x minus 2, right? So that is going to be 3 times 1/3 x minus 2 plus 6. Okay. When I distribute the 3 times 1/3 is 1, so that just gives me x. 3 times negative 2 is minus 6. And then we've got a plus 6, so that works out to x. So it checks out that way, but in order for it to be an inverse, the result has to be x when you compose both ways. So let's try the other way. Compose it this way. This is g of f of x, which equals g of 3x plus 6. Okay, so now in the function g, the x has to get replaced with 3x plus 6, right? So this is equal to 1/3 times 3x plus 6 minus 2. Okay. Distribute the 1/3, so that gives me x. 1/3 times 6 is plus 2 minus 2, which equals x. So when I compose the functions both ways, I get x. So yes, these two functions are inverses of each other. Okay. Let's try a similar approach over here, right? If I compose the functions this way, f, g, right? This is defined as f of g of x, which is defined as f of 5x plus 1. So in the function f, x gets replaced with 5x plus 1, right? So this is equal to 5x plus 1 plus 1 divided by 5, which equals 5x plus 2 divided by 5. And it does not simplify down any farther than this. So this is certainly not equal to x. And so I don't even need to bother trying the function composition in the other way, because it has to equal x both ways. So if it fails the test here, then we can conclude that these are not inverses. Okay. Okay, so now let's go over a procedure that we can follow to find the inverse of a function, assuming that the function has an inverse. So remember that an inverse function does exactly the opposite, right? So basically with an inverse function, all the x values of the original function become the y values of the new function, and vice versa. So this procedure is sometimes referred to as the switch and solve method. And again, remember, it only works if your starting function is a one-to-one function. Okay. The first step, if you're using function notation, replace the symbol f of x with y. Step 2, interchange x and y. Step 3, solve the resulting equation for y. And then finally, step 4, replace y with the symbol for the inverse function, which is that f with the superscript -1 of x. Let's go over some examples where we illustrate this process. Okay. So here we have a one-to-one function, and we are asked to write the equation for the inverse. Okay. So using that procedure that we just spelled out, start by replacing f of x with y. So I get y equals 2 plus 1/2 times x. And then interchange the x and the y variables. So I get x equals 2 plus 1/2 times y. And then solve this new resulting equation for y. So I would start that process by clearing the fraction. So multiply every single term by 2. That gives me 2x plus 4 equals, oopsies, my bad, sorry. Let's back up here. All right. Okay, so 2x equals 4 plus y, okay? And then subtract 4 from both sides. So I get 2x minus 4 equals y. And then I'm going to turn the equation around and replace y with the symbol for the inverse. So I get f inverse of x equals 2x minus 4. Okay? So 2x minus 4 is the inverse of 2 plus 1/2 x. So that's the function that will do exactly the opposite of the original function. Okay. Let's take a look at another one. Okay. In this one we have f of x equals 3x over x plus 1. Okay. So again, following the same procedure, replace f of x with y. So y equals 3x over x plus 1. Interchange the x and the y variables. So x equals 3y over y plus 1. Okay. And then solve this new resulting equation for y. So I would start by multiplying both sides by y plus 1. So I get x times y plus 1 equals 3y. Distribute the x. X times y plus x equals 3y. And then I would basically consolidate all the terms that have a y on one side of the equal sign. So like I could do that by subtracting xy from both sides. That gives me x equals 3y minus xy. And then I can factor out a y on the right side of the equation. So x equals y times 3 minus x. And then I can divide both sides by 3 minus x. So x over 3 minus x equals y. And then I'll flip that equation around and replace y with the symbol for the inverse. F inverse of x equals x over 3 minus x. So that is the method that is used for finding an inverse function. And that wraps it up for this section. So thank you for watching this video.